Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 4 of Analyzing Streamflow Time Series. This is the fourth lecture in the Statistical Methods in Hydrology course. So now we're down to the last topic of longer duration volumes, such as annual volumes, and we'll be talking about dependent random variables and drought. Right, the last time I used these slides was a class in Brazil, and so seca means dry in Portuguese. So when we're talking about drought, we're concerned with long-term low flows, times when flow is less than is required. As we've noted, annual stream flow volume generally isn't independent from year to year, and the reason for that is the connection of stream flow to groundwater. So when the groundwater tables get depressed, they don't recover very quickly year to year. So you tend to have a few dry years in a row before it gets back to normal. So also looking at droughts in terms of just defining drought by periods of time when we have less flow than is needed, they tend to be multiple year events, right? And if we're considering several years at a time, we are reducing our effective sample size. So even if we have 70 or 80 years of data, 5-year droughts will give us at most 15 or 16 events and perhaps less to get independent events. So what we're looking at instead is evaluating dependent random variables, right? So in contrast, annual extremes we were able to describe as independent events, and we're able to do standard frequency analysis on them. Droughts require us to model the flow sequences as dependent random variables, right? So a variable is dependent on the previous period's value. The dependence between consecutive periods is defined as the serial correlation or the autocorrelation. And we're going to take our daily flow values and aggregate into weeks or months or even years, depending on what type of watershed we're evaluating. Right, so we're going to be looking at time series modeling to capture the dependence in our time series. So our goal is to describe the current value of our time series y sub t as some function of the previous value and a model structure and some statistics. So for example, we have our current value and we can describe it as the mean of the time series plus the previous period's deviation from the mean times the autocorrelation, plus some error that shows that we don't quite characterize each value that simply. But we hope that the error is normally distributed, centered on 0 with some variance or standard deviation. Right. So some useful time series models have been formed for monthly and annual flows, but they're really not that effective for daily flows. Daily flows are just a little bit too flighty. So let's look really briefly at some statistics we use to characterize drought. Here we're seeing some annual volumes with the volume on the vertical. The truncation level defined here, we can say is the amount of water that is needed. And so in some years we have more water than is needed, and in some years we have less water than is needed, which could be called a shortage. Now, hopefully we have some storage in our watershed, and so during these years when we have more than is needed, we can store it and maybe pull from storage in these years when we don't have enough. That's the situation we want to be in. But in terms of characterizing drought, we don't assume storage. We just measure the shortages. So here are 3 different drought statistics. We have the duration. So in this case, it's how long stream flows were below the required level. First, we're seeing 2 years, and then 1 year, and then 3 years. The magnitude is the total volume of the shortage across all the years. And then finally, the severity is kind of an average shortage. So it's the magnitude divided by the duration. Sampling error, which we've been talking about already, which is the fact that our sample is perhaps not representative of the distribution we want to estimate. Sampling error is even more of an issue in computing drought statistics because there's very few droughts experienced over the typical record length. And so the small sample means we have a lot more sampling error than we do when we're evaluating high flows. We can address that problem to some degree by looking at stochastic streamflow models. We're going to be looking at this a little bit more later in the week when we talk about Monte Carlo simulation, but first I'll just kind of describe what I mean by stochastic streamflow models. So we use a model like the time series model that I showed yeah, 2 slides ago to kind of characterize the stream flow based on that model structure and the statistics. And then we use the same model to randomly generate possible years of stream flow that follow the same stream flow description of serial correlation. Right. So what is helpful here is that we can use all of the time periods of flow, not just the droughts, but all of the time periods of flow to infer the stream flow statistics. So our mean, our variability, our dependence, or serial correlation will all be used to describe the stream flow statistics. And then we can generate long random synthetic records that will show some droughts, will show some periods of low flow amongst all the other flows. Right. And then we will be able to do our frequency analysis on these longer synthetic records. So the most common streamflow model is probably the autoregressive, and lag 1 is usually enough lag to characterize. And so again, we're going to see this in the Monte Carlo simulation lecture later in the week, Wednesday, I think. So that's it for analyzing streamflow time series. This is the end of the 4th video.